Hi everyone, I'm Akshay. I work for the GPU communications team at NVIDIA, and today I'll be talking about the protocols that we worked on to realize multi-GPU communication across an NVLink network. This is the overall agenda for this. First, I'll present some of the high-level overview of what CUDA support in UCX means and some preliminaries about multi-node NVLink capabilities on NVIDIA platforms. Then I'll try and contrast what was available as GPU support prior to UCX 118 and what are the new sets of features that's available as of 118. Then I'll talk about the performance results, some of the bandwidth and latency benchmarks that we've measured through OSU micro benchmarks, and I'll also highlight some of the limitations that we're working through, and then I'll highlight some of the priorities that we have for the upcoming releases. At a high level, this is our viewpoint of GPU communication stack. At the top layer, we have different frameworks and applications like data analytics, deep learning, and HPC applications that take advantage of different communication libraries. For different frameworks and for the different use cases, there are different necessities. UCX is a communication library that's, in our viewpoint, most well-suited for CPU-centric, GPU-aware communication patterns. These could include send, receive, RMA operations, and active messages. Currently, there are application areas in Spark, in Dask, in MPI, inference, and other new use cases like you may have heard of Q-numeric, which comes under the Liget set of applications, which all use UCX either directly or indirectly. Now, UCX under the hood, it relies on different GPU direct technologies to realize device-to-device communication. And these are realized further over different networks. It could be over NVLink, it could be over NVIDIA network, or it could be over other third-party networks. To talk a little bit about multi-node NVLink capabilities, Grace Hopper platform, a coherent platform, introduced the idea of high bandwidth communication between CPU and GPU through what we refer to as NVLink C2C, where you can get really high bandwidth compared to PCIe equivalent. But not only did they introduce this, but with Grace platform or other coherent platforms, you can realize GPU to GPU communication across OS instances. That's what we identify here as NVIDIA NVLink network. And through this, two GPUs separated by the node boundary can talk to each other over NVLink. And on top of that, there's a feature called EGM, or Extended Graphics Memory, which allows for even memory allocated on CPU to go over NVLink network. Now, unlike regular GPU allocations, which are normally through CUDA malloc, to realize NVLink communication across network, across NVLink network between OS instances, you do have to use a special allocator, and these are in the form of QMEM create or QMEM alloc async, which are more commonly referred to as VMM memory or CUDA memory pools. The notion with VMM memory is that it's a mechanism that CUDA exposes to separate virtual address range allocation from physical allocation. You can separately allocate these two and then have the flexibility of mapping physical allocations to virtual address ranges as you see fit. When you desire cross-node or inter-node OS, inter-OS GPU communication, you do have to associate what is called a fabric handle. When you allocate memory with this fabric handle, then you have these added inherent IPC capabilities that you can then use to take advantage of NVLink between nodes. I'm commonly referring to multi-node NVLink as MNVL here. This will prove useful and for subsequent slides. So talking about current support and current CUDA-aware support in UCX. For internode transfers, we primarily relied on use of GPU direct RDMA. This was either through NVIDIA PRMM module or through DMA buff. But this is also realized on not only IB-based systems, but on other networks. EFA was one of the examples. On top of this, when it comes to coherent platforms like Grace Hopper, since pages allocated on host can migrate transparently to device, we do require such memory to be registered through on-demand paging flag, because we don't want to pin these pages. And for that reason, UCX also enables the use of ODP registrations for host memory when Grace is detected. For intranode transfers, we rely on CUDA IPC capabilities that are exposed. These allow transfers between GPUs within the node, at least until 117. Within the node, when you have two GPUs interconnected either by NVLink or PCIe, you could use CUDA IPC capabilities to move data at a high bandwidth. Further, for intra-process transfers, we use either CUDA memcopy operations, which is invoking DMA engine operations to do reads and writes between host and device, or device and host, or device to device. But in addition, we use GDR copy, which is a capability which allows mapping device memory onto host and then issuing memcopy. Edgar mentioned earlier, MD has a similar capability, but this is exposed as a kernel module that we have to install, and this allows for fast copies between host and device primarily. And for all cases which don't fit into one of these three, where you can do zero copy operations, UCP realizes pipeline protocols, which primarily takes advantage of host staging capabilities. At least by default, when you can do CUDA IPC or GPU direct RDMA, these device buffers are staged onto host, and then they can be moved through any other connecting fabric. Optionally, users can also force the use of device stage pipelining, but this has to be explicitly enforced, and it applies to the whole job. So it's not selectively the case that for a certain pair of memory types, you can enable the use of device memory pipelines. But this changes with the newest release. And lastly, talking about the different types of memories we supported in 117, it was primarily host memory, CUDA malloc, and CUDA malloc managed. CUDA malloc async was supported, but it didn't allow for use of native IPC capabilities that CUDA has under the hood.
So does CPU to CPU still go over NVLink then?
Not with this, not with 117. Because CPU to CPU would, at least with protocols V2, CPU to CPU has scores obtained such that usually something like XPMM or CMA is used within the node. And across nodes, it would be IB that's generally used. IB or any other equivalent network. Yeah.
So, but just for clarification, CUDA malloc async, isn't that a CUDA malloc that is simply enqueued on a stream?
Yep.
So what is the difference that makes it not workable with IPC?
The interfaces that are exposed to extract IPC handles out of malloc async are separate from what are the interfaces for regular CUDA malloc. So that was the only difference, and we hadn't. It was just a matter of having not been implemented.
Okay.
Yeah. With 118, on the internode side, ODP v2 has been enabled by NIC firmware by default, and so on coherent platforms, we not only register system allocated memory, things like malloc and POSIX memory line, with the on-demand paging registration flag, but we also do this with CUDA malloc managed. for the same reasons, because these pages can migrate between host and device, and we don't want to necessarily pin down these pages. In addition, we now support the ability to pass any memory, whether it's host or malloc, CUDA malloc manage, malloc async, or CUMEM create, to UCX and MPI buffers. And all of these use multi-node NVLink capabilities in some form or the other. There are constraints, and I'll talk more about those, but in summary, they take advantage of multi-node NVLink to the best extent possible. And some of the changes besides UCX, what features are provided by UCX 118 that's required is we do require OpenMPI 4.17 or 506 because we added changes. Edgar, you were part of this.
So for multi-node, you would like to use NVLink because it will give you better bandwidth because of the switch?
Yeah. There's a higher bandwidth path available. So if we can use that within the node or across nodes, if the reachability exists, then we try and take advantage of that, especially given the fact that the path between CPU and GPU is now a much higher bandwidth path through C2C, as opposed to on non-coherent systems where you just have PCIe. Even if you had NVLink capabilities across GPUs, you couldn't take advantage of that for host because your slower path is the path between the host and the CPU, and it would be slower. The other main addition, and I have UCX Core was instrumental in this, which is they've now in Proto V2 natively has the ability to use either host or device stage pipelining protocols based entirely on scores. And UCT has this interface, as you may know, the perf estimate interface, which allows you to specify bandwidth capabilities between memory devices. Protocols V2 takes an overall look into the overall bandwidth that you would get from using different paths, and it makes an optimal choice of whether to use host or device staged buffers for as fit for the given source and destination memory types. And so with this capability, we are now able to move not only VMM or the new memory allocations with fabric memory types through NVLink, but we can also move CUDA malloc host, CUDA malloc manage, also through multi-node NVLink, even though they don't natively support multi-node NVLink capability. In addition, when the user passes CUMEM create or malloc async memory without fabric handle, we can still stage that through library internal bounce buffers, which have the fabric handle capability. So we're basically in all three cases, we end up taking advantage of multi-node NVLink. And this is possible thanks to the automatic staging decision that UCP Proto V2 has now. So coming to performance results, they're mainly obtained from extended OSU benchmarks that they make use of VMM API as well as memory pools. And I'm just using these notations. When I say FD, which it refers to fabric print device memory, which is nothing but CUMEM create memory that has the fabric capability, which is allowing for native use of multi-node NVLink. FMA is the same thing, but it's memory pool buffers. And D refers to CUDA print device, which refers to the legacy CUDA malloc memory. I'm also going to discuss the impact of the fragment size on the overall pipeline bandwidth, because that's something that we have to resolve in UCX. And finally, I'm going to also talk about GDR copy performance, the importance of GDR copy on even systems like multi-node NVLink systems. So to start with, this is MPI unidirectional and bidirectional bandwidth. On the left-hand side, we see how the three memory types, or if it's VMM or stream-ordered memory or CUDA malloc, how they fare. And for baseline, VMM and malloc async memory, they go through native multi-node NVLink capability. They don't go through a staging approach. It's only the older CUDA-Malloc memory that goes through staging. And so you can see that with increasing size, when zero copy is used, more or less you get a saturation and not a degradation in performance, and it reaches close to speed of light. The same is true with bidirectional bandwidth for VMM memory and malloc casing, but not the staged approach. And on the left-hand side, we see the reason why. The main reason is that the UCX default fragment size is 4 megabytes, which is not enough to saturate NVLink, which has a much higher bandwidth than what is, and so you need to push it up to closer to 32 or 64 megabytes realistically to try and reach the saturation point. And as you can see here, when this is on the left-hand side, we have graphs where I vary the fragment size and then compare to just the VMM allocation capability, which is what we consider as the speed of light here. And as we increase fragment sizes, we see that the pipeline efficiency improves.
Where do you change the fragment size?
So each of these colors, they represent the same memory types, which is CUDA-Malloc to CUDA-Malloc, starting with 16 megabyte, then 32, then 64, then 128. These
I think we can see your mouse.
Oh. Yeah. So we have 16 megabytes here, 32, 64, and 128. As we increase the fragment size, we can see gradual improvement in the pipeline efficiency over different message sizes.
So the overhead of copy operation.
It's more because 4 megabytes, which is the default fragment size, is insufficient to saturate NVLink bandwidth.
Yeah, but why? What kind of overhead is important? Is it the CUDA copy?
Yeah, CUDA memcopy only reaches like the peak saturation at something close to 16 megabytes, like or 32 megabytes, which is why we do need to push up the default fragment size.
In all cases or just in specific?
So we can see, so here on the left-hand side, right, we have what happens if we just use fabric device memory, which is zero copy, basically zero copy performance. And we can see that this actually saturates closer to 256 or 512 megabytes. So that's really when CUDA memcopy async is able to fully saturate NVLink.
But that could be a problem because it's memory usage.
It's high memory usage. So this is something that applications may have to tune, because in art, if the expectation is that they reach full saturation of the link for a given for a single transfer, then they may have to increase the fragment size dramatically.
First of all, I think we don't want to make applications tune such things.
Right.
Second, maybe if you have, not sure if it's important, but you have multiple processes, multiple threads, still not needed. Also, maybe depend on user buffer size. If user buffer is small, not need to allocate huge fragment.
No, absolutely. And I think the things that you mentioned, by default, I think what we have suffices, and in most cases it should work. But if there are cases where applications want to see higher bandwidth between pairs of processes, then they may have to tune the fragment size.
Is there a way like to pass scatter-gather list to put a copy?
No. But so there is a public API out now, which is called CUDA batch memcopy operations. They allow for multiple sources and destinations and lengths to be passed. So there's an option to consider using that, and it does drive down the driver overheads of issuing each time, but it's still not fully applicable for a pipeline transfer, because in a pipeline transfer, we do want to enqueue these operations onto streams as they complete.
Yeah, but you could avoid allocating huge chunks of memory, and you can take as much buffer as needed according to user buffers.
Yes, I guess what you're saying is that we could potentially consider reuse of the same buffer, because we know operations finish in stream, and when one of the preceding operations complete, we know the
Not,
buffer.
not reuse, but let's say you allocate 4 megabyte buffer,
Mhm.
and we know that user buffer is larger than that. We can take 2 buffers from the pool,
I see.
and the pool could be like pool of 4 megabyte buffer. Even maybe even smaller. I'm not sure what's
Okay, yeah,
Over.
that's definitely,
instead of creating a pool like 32 megabyte buffers, which would consume a lot of memory, especially on GPU.
mhm. That's definitely an option, yeah. That said, I don't know how this would be realized using UCT API because the pipeline relies on UCT zero copy operations.
Actually, I think it should work because the target is the user buffer, which is a single pointer, and the source in zero copy is a IOV list. And you would use UCP get the copy to copy from a user buffer to the bounds buffer,
Okay.
and then you can pass a local IOV list.
Does zero copy operations also have an IOV
Yes.
option? Okay, then yeah, it should be possible to do that. Yeah, we can think about realizing IOV functionality using batchman copies. Yeah, to be noted. Okay, to get back, I think I just wanted to highlight one more thing, which is this selection of fragment size has a much more pronounced effect in the bi-bandwidth range. As you can see, device-to-device transfers with CUDA-malloc, it reduces a fair bit with default fragment size, but as you push up the fragment size, your bi-bandwidth efficiency goes up.
Does it make sense to somehow put a copy on a separate thread or something like that?
Putting it on a separate thread is the idea to launch many of them and not be hitting the overheads in the critical path.
Yeah.
Yeah,
Especially if it goes to sleep and they kind of waits for the driver. So it would be truly async and over. Because in bidirectional, I think the issue is like blocking the code.
Well, actually, the issue of the copy itself is not the problem, right? The issue is non-blocking. We do issue those copies and wait for it in some request wait operation.
And there is no overhead on the current thread.
There's some overhead, which is like 2-3 microseconds. That's the overhead of just issuing the man copy operation. Yeah, what you're saying would make more sense if the whole overhead of, progressing the fragment itself wasn't the critical path. But since we use streams, this is all basically unqueued.
Okay.
But we should think about the use of batchman copies. I think that could be a useful way to not have high fragment sizes.
You have a thread that gets the copy work and can maybe collect batches even from unrelated operations.
We could do that, but there's also this notion that we have in CUDA IPC of us having separate streams. Right. So
do not create deadlocks.
Yeah, so we may have to consider some implications there, but we can think about like what would be the benefits of moving it to a thread or through the batchman copy.
Okay.
The next set of graphs I want to show was with considering the importance of GDR copy even on systems like this, because while you have NVLink capability between GPUs across nodes, you still have to use IB-based techniques and GDR copy techniques in order to realize low latency between these GPUs, because just going through NVLink is still going to incur the same driver overheads that you would incur. And you would see, even though there's high bandwidth, there could be larger latency if you just use NVLink between nodes, even for short messages. So what we show here is what happens when we use GDR copy with CUDA-malloc. Without GDR copy, we see the latencies in between 8 and 10 microseconds, but you can get it close to 2 microseconds or 2 to 3 microseconds if you use GDI copy on both sides. So just start trying to highlight that even on systems like this, you still need to continue using GDI copy. So some of the limitations with 118 are as follows. To use multi-node NVLink capability, there is an environment variable that we have to set today. I think we'll be relaxing that with the PR that Mikhail is working on. The other drawback, because of limited testing, is that we support EGM or extended GPU memory only as an experimental feature. This is the virtual memory that is backed by host, where technically host-to-host transfers can just go over NVLink, and this is supported. There are some corner cases when this is mixed with IB where we see some issues. So this is supported as an experimental feature. If you're only using systems with just multi-node NVLink capability and maybe something like TCP, then it should be perfectly fine to use, but you may run into some registration issues if you decide to use EGM and IB. The next drawback is that some of the device pipeline paths, they're suboptimal in end-to-end bandwidth. And there are Mikhail and others from the UCX core team are actively looking into this, and we've investigated some pipeline efficiency issues at our end as well. So we are looking to address this through driver and through protocol soon. Finally, I did want to highlight that there may be a need to tune fragments, but Yossi, we should talk about the proposal you had about bashment copies and potentially using an asynchronous thread. Looking forward, the main priorities for us are Blackwell support. We have working implementations. It's a matter of making this public. We also have on our roadmap to allow for a single UCP context to use multiple devices. Today, we don't have, primarily the modes that's supported is a single MPI rank or single process or a single UCP context manages one single device, but this is limiting for many use cases, and many applications have already worked around this, but with growing use case, we want to relax this requirement. The other thing that we are prioritizing is to not have process set a GPU context before it makes any MPI or UCX calls, because this has been painful for multiple frameworks. And so we are actively working on adding the necessary support in CUDA transports and potentially elsewhere to address some of these hard constraints. And lastly, there has been for some number of years, we've had issues with CUDA IPC resulting in memory leaks. And this occurs because CUDA IPC directly maps user buffers. And when a user buffer is mapped under the hood without user's knowledge, and then the user feeds that memory, this can lead to undefined behavior and often results in leaks. So we are trying to address that using some techniques in ProtoV2 as well. Those are the main priorities, and that's my talk. I'm happy to answer any questions if people have.
I'd like to extend on the 119. So the multi-device support actually has a lot of implications more than this one line to capture. The most basic thing is to avoid the need to, in the application, to set the right GPU context. I guess it's something that has to be in the CUDA level. I'm not sure if it's relevant also for Occam, but it's something that should be solved on the GPU support level. Also, want to improve the protocol so they would be able to select the bounce buffers on the right device. Currently, we have a hash table that Ashkay added. It's only according to the memory type.
Memory type.
Yeah.
We don't use the GPU type.
We have it there, but it's not really doing anything.
Right.
We want to be able to allocate buffers on specific GPUs. Maybe we want to extend the UCT memory allocation API for that, so that GPU layer would be allocates on a specific device according to the user buffer that users provided. Everything would be created on demand, etc. And the third aspect is that the connection establishment phase. That today we create lanes between pairs of network interfaces. We don't create connection between all possible pairs of the network interfaces. And that may be an issue if we want to send the buffer from one GPU to a device, to a GPU on the remote machine, but they don't happen to have a network queue pair between them. There are several approaches to handle that. One is something like PXN, where we copy data on one of the sides. Another way is to create all possible connections, but that also has its own implication. Another approach that we considered is, well, actually it would be a pretty major change, but to move to something which is more similar, I think, to EFA or something in PAMI, where the endpoint is not something persistent, but we could send to a specific address on the fly, and then the number of things that you have to remember on the UCP layer is not the n square, like the number of total possible pairs, but only the number of possible remote destinations. And then you could send the same destination handle from different local devices without the need to create a handle for each possible pair of phone.
So the last one, how would that be realized in IB, Yossi?
Only several, probably not all transport should support it.
Right.
With this transport, it's quite easy.
Right.
Just need to remember the remote address, and then, well, putting aside all the scheduling stuff, you could just send work requests to the remote address for any local device. I mean, generally speaking, with UD, we must hold the state. With RC, you also must hold some state.
And I know we increased as an intermediate solution at some point.
We want to increase the number of lanes, but
Right.
that's not scalable
Right.
long term. Because just for 8 devices, we need 64 lanes. And if we have multiple connections between each pair, then problem. But we were starting from that.
So for the upcoming release, like say 119, what's the best or most reasonable candidate?
Or all-to-all connections, or maybe something like PXN.
Okay.
With PXN, are you looking at just mainly like one hop as an intermediate hop, or like is it up to n hops?
Sorry, I didn't.
With PXN, are you looking at like one hop max, or like are you looking at like maybe 2 hop, 3 hops?
Which kind of hops do you mean?
Between like as an intermediate node, like when you're staging to another buffer that has a full connection.
Yeah, so PXN, I meant to allocate a buffer on a different GPU.
Yeah.
Use a NVLink probably, could IPC to copy to that, either on the source or the destination, and so we could eventually use the existing connection.
Is it always expected that that copy you only need one of them, or will you potentially need 2 to get to the endpoint that you're?
Or just one of them, because eventually it's like a rail optimized system. We were always able to reach to each device on the local or remote, but just not necessarily it will be the same one.
Yeah, makes sense.
I have actually a question for MD folks. Is the context issue also relevant for ROCm?
No, not really. We don't have a context on the runtime level. So from that perspective, I think until recently, I had little worries from the UCX part for us to support multiple GPUs. Now with the pipeline protocol that basically uses GPU buffers, that's a different issue, right? Because you need to make sure you allocate it on the right GPU.
Yeah.
And I was actually more worried also about the MPI layer side of that.
Also,
Well, if you allocate a stream,
Mhm.
is that bound to the device that you currently had set as a current device the moment you allocate it?
It is.
If that's the case, then for example, the entire OpenMPI card logic right now is because of that single device. And that requires a very significant change on the MPI side, right? I mean, I understand that for UCX, if you call the UCX path, that doesn't come as much into play.
Hmm.
But for every other device, basically, it is a problem.
Basically, when you, something like UCX or when something like libfabric isn't used, when OpenMPI is natively supported.
Yeah,
Yeah.
so with libfabric, as far as I understand, the CUDA support through libfabric, they are actually, well, okay, let's put it this way. For some pipeline protocols, I think the stream copy operation of OpenMPI would come into play there as well. And that's like a CUDA mem copy async. And so the stream that you allocated would matter.
Mhm.
Yeah,
You mean in the context of data type packing?
for example.
Edgar, you mentioned that the runtime doesn't expose context,
Yes.
but are there implicit contexts? Like when, I mean, the same is true in CUDA as well. Like it doesn't expose an explicit context object, but when you call APIs like set device or
On the
CUDA
runtime
malloc.
layer, we don't have the notion of an active device.
I see.
Right. So you see a certain set of GPUs. In theory, you could use any of them that you can see. Yeah. And one of the hacks that we have currently in UCX, and that's the one thing that I'm also in addition worried about, is that for the allocation in the CUDA copy component, we keep track what was the last CUDA malloc that we intercepted, and that's the device that we will be using.
Mhm.
Yeah.
So is there like a CUDA malloc equivalent, like a hip malloc? Does that take a device as an argument, or does it implicitly?
So on the hip layer, you have hip set device and then hip malloc, and you will allocate on that device.
Okay.
On the runtime layer, the HSA functionality doesn't have that notion. So you intercept an HSA memory alloc from pool or whatsoever, right?
Okay.
And all of the hip malloc functions are mapping to that HSA functionality.
Okay.
And there you need to know the memory pool. But a single device can have multiple memory pools.
Okay.
Yeah.
Do you eventually want to pipeline for a device that is closest to the user memory, right? So the user provided pointer.
Yes, I mean, we intercept those calls and we basically keep track of what was the last memory pool that was used in our interception.
What does it tell us?
That's the device that we would allocate a temporary buffer on.
But is it good enough? I mean, would you want to like check the pointer somewhere and check which device it belongs, to which GPU it belongs, then allocate the buffer on that?
So, but that in itself is not enough because that one device again can have multiple memory pools. Yeah.
But would the performance of memory pools be different on the same device?
It could, because we have this notion of fine-grained versus coarse-grained memory, which gives different
It changes the caching behavior.
cache coherence guarantees. Yeah.
So the best way with Rock'em is to know more about the buffer than just its device.
Seems like you need to know which memory pool that the buffer came from so that you can sub-allocate from that memory pool as a bounce.
Yeah, so as long as we're using one device per rank, I think I'm fairly confident that we should be okay with the current solution. But the moment we would extend it to multiple devices, I think in that case we need some additional.
Is it important for your use cases to use multiple devices per rank?
API by which we can check.
Right now, probably not, but I could imagine that in the future it will become more important.
Including to the
Another unrelated question, or maybe a bit related. You mentioned that the previous presentation,
I haven't tried to
OpenMPI stuff that you're working on, including the data packing and packing today, probably doesn't work well because it's back into host memory, right? And unless, at least with UCX, if you're using non-contiguous buffers, you have to back into host memory and use this stream data type, or you have to back yourself into some bounds buffers on the GPU. You see that as something that is important to improve.
Yes, but that requires significant extensions in OpenMPI as well. So I mean, George Bozilka, who is I think in your group, I mean, he did develop like a kernel that could implement pack-unpack operations on the GPU itself. Because I think that pack-unpack you cannot issue from the CPU side in order to make it more effective. So if you want to pack into GPU buffers, it would have to be something like a GPU kernel. So that's, I think, again, would be interesting, but it's a significant extension to what needs to be done there compared to what we have right now.
Okay.
From our side, like there are use cases in OpenACC, OpenMP, where the notion of using multiple GPUs is abstracted away. So different threads could be managing different GPUs based on the function that they're going to execute down the road. So for those reasons, this is becoming an increasing priority, having multi-device support.
We have one more question online. Amir, can you hear us?
Yes,
you want-
can you hear me?
Yes. Do you want to go ahead and ask your questions?
Thank you. That was a great presentation. I have 3 questions. The first one is about, you said something about batching small data transfer. Well, using CUDA MCP like 2D and 3D probably. Is it something, are you talking about the same thing?
No, it's not. There's a newly publicized set of APIs called CUDA batch mem copy operations.
Okay.
These are different from the 2D and 3D versions that you talked about. I
Alright.
can put a pointer on the
Thanks.
Yeah.
And do you think it's a good idea to have that capability in UCX if the user requested to batch the data transfer and combine them before setting them off the wire?
Yeah, this was Yossi's suggestion too, that we could take advantage of UCT's IO vector feature and basically describe multiple sources and destinations and lengths. And then you could essentially realize that in a single copy using this batch mem copy operation, wherein you infer the arguments from the IO vector.
Oh, I see. That's great. Okay, the other question that I have is, first of all, this is a silly question. How does device stage work, device stage transfer? Are you actually using other devices to stage the data there first and then use that for staging area?
We try to stage it on the same device. Like in UCX, there are memory layer functions to detect the memory type and memory location of a given user buffer. And from that, we can make a choice about on which device do we want to allocate bounce buffers so that we can stage user buffers onto those bounce buffers and then realize the pipeline. As Yossi mentioned today, that is not smart enough to handle different cases. It handles the simple case where a single process only manages as a single device. Tomorrow, if it happens to be the case that the single process is managing multiple GPUs and it's managing multiple user buffers from multiple GPUs, we need to extend the existing allocation API to also include on which GPU do we want to allocate these bounce buffers so that we can stage each of those buffers closest to the location where they're residing.
Oh, that's great. Thank you. And then my last question is there any plan on your roadmap to handle MPS-enabled GPUs where multiple processes are on the same GPU so that they can handle data transfer more efficiently?
So
actually, I don't think we need anything special in UCX.
right.
Our CI machines currently use MPS to have a better support of multiple testing concurrently. So it just works.
Yeah, MPS is tested and there are applications that already use MPS, so it should work.
Okay. Okay, great. Thank you.
Is there anything else?
More questions?
Let's check online if you have any more questions. No, I don't think there's any pending questions online. Thank
So
you.
to add one more complexity, if we would add something like a device ID to some of these allocations, I don't know how that is on the CUDA side, but for us in theory, there could be scenarios where what the user sees as HIP devices, the order is different than what we see on the runtime level. Right? The user can modify the list of devices, for example, by setting HIP visible devices. And on the runtime layer, we get, however, the list as provided by the system.
By the way, a more general note. So in CUDA, we moved away from using runtime API. We just use driver API. I think at some point it was a mix, but it caused its problems. Maybe you should consider a
So what for us is the runtime is for you the driver. That's the level
That's a good
below the programming API. Yeah. So
Drivers in VML.
maybe.
So in as it stands, right? Like we allow users to manipulate visible devices list the way they see fit. As Yossi was mentioning, we would simply query the buffer for its memory type and for the resident location. So we'd get a device ordinal from that buffer. So by knowing the device ordinal, you can always know where to allocate it.
yeah, so if we would use the UCX functionality the way it is right now to detect buffer type, that would work.
Okay.
It's basically my worry is we cannot use the information coming from the application because that numbering scheme might
Yeah,
be
the
Oh, yeah.
application, we don't even want to get any information from the application except the pointer itself.
Yeah, we don't use that today.
No.
Okay.